This video we're going to talk about electric potential energy. And so the picture I have here is a picture of a capacitor, and basically at the top here you have a plate that's filled with positive charge and then a plate here on the bottom that's filled with negative charge. And because there are charges here, there's an electric field between the two plates. And the really cool thing about capacitors is that the electric field between the plates is constant throughout. So if I have the electric field at the top over here is the same as anywhere else, which makes some of the calculations a lot easier. So let's think about electric potential energy. So we have P1, P2, and P3. And if you remember from gravity, the potential energy, the change in potential energy is the negative of the work done by a conservative force, like the electric force, for example. And you can think about that as if I had a pencil on a desk and I lifted it up, right, I did work against the conservative force, right, so I gained potential energy. Now if I drop that pencil, the conservative force does work on the pencil, right, it's falling, so it's losing potential energy. And again, just good to remember that. So if you're doing work against a conservative force, you gain potential energy, right, you're like adding money to that bank account of potential energy. But if you're actually using that potential energy, right, if the conservative force is doing work on you, then you have to be pulling energy out of that, what I would call a bank account of potential energy. So let's think about potential energy in this instance. So remember that work is force times distance. Well, in our case here, force, remember, is Q times the electric field, and D really is kind of a height here in our circumstances. And so this QEH is very related to the potential energy. So say I have a positive charge and I put it here at P1, it will feel a force, right? And we could figure out that force by multiplying whatever charge it had by the electric field at that point. And we're saying the electric field is constant throughout, okay? And we kind of can just tell that, well, because there's positives above it and negatives below it, it's going to go down, right? It's going to be repelled by the top and attracted by the bottom. And the force will be constant the whole way through because the electric field is constant the whole way through. But if we think about what has more potential energy, P1 or P2, right? Say I put a positive charge at P2. Well, the same force will be on them the whole time, but we can see that the distance that P1 will have to, like, quote unquote, fall is much bigger, right? So it has more potential to fall, or there's more distance over which the electric force can act over it. Therefore, more work is done on it by the conservative force. But that means that it must have had a lot of potential energy to begin with. And so we can see that the potential energy, the P1 has more potential energy than P2, which has more potential energy than P3, because P3 has the least amount to kind of fall, right? It has the smallest distance that work can be done on it. Or I'm sorry, smallest distance that a force can be acted on it, which means the smaller amount of work that can be done on it by the electric force. Another way to think about it is, well, let's say, well, if I put a positive charge at any of these points, it all end up kind of stuck to this bottom part, this negative part of the capacitor. Another way you can think about it is, like, well, what if we had that charge and we wanted to move it to P1, right? How much potential energy would it get if we had a charge on the very bottom and I wanted to get it to P1? Well, now you're going to be going against the conservative force, right? The electric force is like, hey, go back down, and you're like, no. So you're taking it and you have to put it in your pocket, and you might have to walk all the way up here. And you have to do a lot of work to do that, which means that you're doing a lot of work against the conservative force, which means that it would gain a lot of potential energy by the time you got to P1. And you can see, likewise, that if you only had to walk to P3, you wouldn't have to put as much work in, which means it wouldn't gain as much potential energy. And P2 would be in the middle. All right, and now one important thing to look at here is that we can also start thinking about this in terms of potential energy per charge and what that would be like. And just you can let that marinate until the next video.